All right. Well, happy finals week or almost finals week if you're starting this thing off early. So I just wanted to take a couple minutes to quickly kind of sketch out some of the goodies that you're actually going to see on this second exam. I'm actually hanging out in Beacom right now, so I don't know if the recording is going to sound really weird. It's super duper echoey in this room, so we'll see what it looks like on the back end. So anyway, here's what it looks like. It's going to be exam 2. What you can see on the very top is that you only have to do 9 of these things. So you can actually cross off one of them if you don't feel like working on it, or you can go ahead and do all of them, and I will throw a few bonus points your way. So the first few questions on this thing are fairly cut and dry. I basically took some of our old activities and I just reconstructed some new little graphs, and we can play around with these questions of reachability. So the first one is going to have this graph that has 10 total vertices, so labeled 0 through 9. We're going to be running some breadth first and depth first search processes on these. So I want you to basically see where you can get from this initial source 0. Here you can actually see that this graph is nice and connected, so everything will be reachable. So then the question becomes, how many steps does it actually take to get there? So in part A, you're just going to try to build that little tree. So you're going to have this idea that you're going to have 0, and then from 0, I can get to 1 and 3, and then keep that process going as you see fit. At the end of that, you'll be able to easily see what things can actually be reached within 3 steps. Basically, everything 1 click away from 0, everything 2 clicks away from 0, and then everything 3 clicks away from 0 will nicely fit into that little bin. You can do it depth first wise, and then ultimately we're going to build a little adjacency matrix for this thing. So that top row you're going to be thinking about, that's going to be 0 out to other stuff. So 0 is connected to 1 and 3. So a 0, 1, 0. So 0, 1, 2, and 3. So if I think about labeling 0, 1, 2, 3, and so on. So you can go ahead and sprinkle in all of those little ones. Eventually, we're going to run this thing through some power mod or some power matrix functions. So if you want to just do this all in the Replit or in Python and not have to hand write it all out, I'm totally happy with that. Sometimes it's obnoxious to hand draw all of these things, as well as when most of it's actually going to be 0. So if you want to hand draw this thing and then transfer it over, that's totally fine. If you want to just type it up and then give me copies of that or screenshots of that, I'm totally happy with that as well. So once we know this little matrix, we can begin computing powers of it. So we built up this power matrix function, which is the same type of operations that we use when we can go ahead and actually compute this power mod operator. So here we're going to compute a to the 3rd power as well as a to the 4th power. So if we look at that top row within A3, that's then going to tell me the number of paths that are going to start at 0 and then end at individual little slots. So if I want to think about the number of paths that are going to go from 0 to 9, what I'm going to be looking for is that top right corner in A3. Likewise, if I want to think about paths of length 4, I'm then going to compute a to the 4th power, and then again study that top right corner to give me those paths from 0 to 9. So that's going to give you the number of them. Then you're going to have to go back to the little graph and actually start counting them out. So you can see that a path from 0 to 9 is 1, 2, 3. So 0 to 3 to 6 to 9 would be then one of them. And you'll see exactly how many you're supposed to have, and then actually go out and write those things. In part 2, you're going to be doing basically the same thing, except for I've changed it to a directed graph. So I've put little arrows on everything. So you're going to see some directionality. So if you zoom in really close, you'll see some arrows. And then after that, it's basically carbon copy. The only thing that changes is that when we build the adjacency matrix up, it's no longer going to be nice and symmetric. So the idea here is that it's going to be starting at 0 and then going somewhere. So 0 is connected to 1, but 1 is not connected back to 0 because we had that arrow going this way. So it's going to be a little bit different. So what I'd recommend is obviously take this one that you had before, because all of these edges are the same as what existed up here, except for I've added in some directionality. So you'll see this little a is going to look similar to the a before, except for we've erased some of the ones. So same game as before. If you want to just go ahead and type this thing, I'm totally happy with that. If you want to hand draw it and then transfer it over, that's totally fine as well. In problem 3, we're actually going to revisit one of the nice little Markov chain problems that we saw before. So here's where I'm actually going to copy and paste one of the things that we had in homework 4. So here we were playing this game of pennies, where both parties start with 2 pennies, and then we have to pass them back and forth. In the homework, the game of how we switched pennies was by flipping some other type of coin, and then comparing if they're both heads or heads versus tails or things like that. Here we're going to change the game up by introducing rock, paper, scissors. So standard rock, paper, scissors rules where rock beats scissors, scissors beats paper, and paper beats rock. Whoever wins this thing is then going to receive a penny from the opponent. So if we both start with 2 pennies, the first example is where Eve is going to throw rock, Bob is then going to throw scissors. So rock beats scissors, so Eve is then going to receive a penny. There's a fun little twist to this, which is actually a student submission. If you remember back to this homework, I had the idea of, hey, give me a couple of examples of other fun modifications to this. So one of the fun modifications that a student proposed was if you have a tie, so double rocks or double paper or double, what did I already say, rock, paper, or scissor. So if you have any match of those, you're not going to just say, whatever. You're actually going to swap penny piles. So if one person has 1 and one person has 3, then those are going to flip-flop. If both have 2 and you both throw rocks, then obviously swapping penny piles is going to essentially do nothing. But if you're in the lead and a tie occurs, then all of a sudden you swap those. So it does make for a fun little variation to this game. So as before, you're going to sketch out the little diagram for this. So you're going to have some transitions. Here we're going to have the chance of going from state to state to state is then going to be based off of your chance of winning rock, paper, scissors, which here is going to be about 1/3. In the later parts, you're going to then shove it into this transition matrix, compute massive powers of this thing, and then essentially study those far left and far right columns. They're going to tell you what your probability of entering a win state or a lose state is, starting with 2 pennies, or what happens if you start with 1 or 3 pennies. On the second part of this one, we're going to change it just a little bit. So if you remember back to the homework, we had this game of flipping pennies or flipping things like that. And we maybe would have some, initial choice that we're going to sway some things if we're thinking that we're going to lose. Same thing is going to happen here, is that if we're ever down in a state where Bob has 3 pennies, the claim is that he is more likely to throw rock. Well, if he's more likely to throw rock, then you are going to always throw paper. So it's going to change up some of those probabilities just a little bit. So before you had these thirds across the board, now you're going to start seeing some different numbers. So some quarters and 50% coming into play as well. So you should be able to basically take the same exact structure that you had up above, change some of those probabilities up just a little bit, re-execute these massive powers of this matrix, see those left and right columns, and then see where those probabilities of success are then going to ultimately land. Problem 4 is legitimately a copy and paste of an earlier activity. It's this cool little crypto system that we built out of these error correcting codes. I just wanted you to run it one more time. Basically, I had a little bit of blank space on this page. So I was like, all right, whatever, just rerun this thing, see what it looks like, and have fun with it. So you should be able to feed some of these things into some of the starter code that I have. The only thing that you're going to have to design is then going to be whatever your favorite little 4x4 permutation matrix is going to scramble up the rows, and then also the n by n to go ahead and actually scramble up the columns. After that, by all means, use the little program that we built up to actually compute what these new little matrices are going to be. Go ahead and hand change some of those bits, send that thing across, and then run this decoding process to see that it actually does in fact work. So this is nothing different than what you had in the activity. I just wanted you to do it one more time because we spent a little bit of time building up this crypto system, so I figured it was worth running one more time. And I kept the numbers small so you could at least hand write them rather than have these giant screenshots of epically large matrices. In problem 5, we then revisit this notion of bad hashing. So we didn't actually have an activity looking into some of these hash things just because they all ended up being kind of boring. It's like, all right, we built up this bad. We talked about collisions. We chatted about some of these message digest families. Cool. What do you want me to ask about it? So I chose to revisit this game of bad hashing just to get us working with some of these operators, basically working with the XOR and spinning things around. So the original bad hash algorithm that we had was to just take all of the entries and then just XOR them all together. So it just took whatever message you wanted and then distilled it down into this final little 8-bit digest. So we just XORed these things across the row. So that is this piece of operation, which would be to take the next thing in this Unicode structure and then just XOR it. Just keep on crunching that down as we go. The new twist to our second version of bad hashing is going to be to do exactly that, except for after you get that new value. So you take the first value, you take the second value, you XOR them together. Then what's going to happen is I'm going to take that value, I'm going to reverse the bits, and then XOR those two things together. So I have a working run through of me hashing the word hash. So 72, 97, 115, 104, which then I can represent as these nice little 8-bit objects. And I'm actually going to pick it up in what is going to happen in round 2, because round 1 is kind of boring because it starts off with an initial value of D as 0, and then it doesn't do a whole bunch. So in round 2, it's going to come in with the D being 90, and my A then corresponds to 97. So I represent those as those nice little 8-bit numbers, and then I XOR them together, which is what this operation is over here, which is this line in the thing you saw. I like doing the operations stacked, but when I actually write them out on this page, I'll write them horizontally because I don't want to take a ton of space. So you can see that that 90, so 0, 1, 0, 1, 1, 0, 1, 0, XORed with 97, so 0, 1, 1, 0, 0, 0, 0, 1, then kicks out 0, 0, 1, 1, 1, 0, 1, 1. I'm going to take that object, so that's going to become that thing. I'm going to reverse the bits, which is then going to become that thing, and then I'm going to XOR those two things together. And then that's going to be stored as my D value in the next iteration. So you're still going to essentially work left to right. So you're going to first play with that thing, then you're going to add in that, then you're going to add in that, then you're going to add in that. But when you add them in, you're going to first XOR it with whatever that current digest value is, then flip the bits and XOR those things together. What's really fun about XORing a thing with the reverse version of it is that it always kicks out something nice and symmetric, which is cute, but it's also very, very problematic. So here we ended up seeing 1, 1, 1, 0, 0, 1, 1, 1, which obviously when I flip the bits and stack them all, we're going to get this nice symmetry, which is going to take this game that was already supposed to have a ton of collisions and even further kind of distill it down because we have fewer possible digests to emerge. The only possible things that can exist on the back end here are going to be these symmetric 8-bit numbers. So initially we had 2 to the 8th of them, and now we have fewer of them because we're avoiding things that would be a 1 followed by 7 zeros. That's not an actual possible output anymore. So what I want you to do here is to run this bad hash algorithm on the word cyber with a capital C. So basically XOR these things and then flip and then XOR. So run those things 5 times. I'd like you to at least do a couple of them by hand just to make sure that we know how this XOR process all goes down. In the starter code, I do have this bad hash algorithm version 2 sketched out so you can see what the output is supposed to do. But I would like you to at least do a couple of them by hand just to make sure that you know how all this fancy XORing and bit reversal works. And hopefully in the back of your head, it is screaming that you want to do this on a Turing machine. Maybe it's not screaming that you want to do it on a Turing machine, but you totally could. So earlier in the semester, we chatted about some of these bit reversal processes. You can easily do XORing on a Turing machine. We chatted about addition on Turing machines, so you could do addition without the carry side of things, which is the XOR process. And then you could design this whole entire hashing algorithm in the little turingmachine.io site. It'd be super duper awesome if somebody did that. So there's your challenge problem, which is the little bonus that I have on the bottom, which is like, you totally know you want to do this in a Turing machine. So please do, because it would be awesome to see. At least for a fixed input, just like take the word cyber and bad hash it there. So that's part A. In part B, I want you to just play around with that implementation that we had, just make sure that it does in fact work. So that's the verification stage. And then in part C, we have this laundry list of things that we're just going to generate some words. And then we're going to try to see if a list of 16 is actually going to have some collisions. So in the early version of the bad hash, we ran some versions of 16 things and we saw, some of the time, so about 30% of the time, we would get some type of collision. This one, you're far more likely to get collisions because, again, the output space is much smaller, is that they have to be symmetric. So when you run this in part C, you'll see a ton of collisions. You should see a ton of collisions. So to sketch out a few words that actually collide with the same thing, if you'd like to come up with some other examples that are going to hash into the same thing as cyber, you can sort of play around with those as well. Same type of issues happen that we did before. Basically, have some double letters, add a couple exclamation points. All of those things are going to XOR into the same thing, so it becomes problematic. Cool. All right, so in problem 6, we were playing around with the game of life, which is a 2D version of this cellular automata. So I decided to scale this back just a little bit to chat about the 1D version of this thing, which creates equally cool pictures, except for the pictures here are not typically drawn in this flip book fashion. So that's what that little block of text is all about. In the normal Conway's game of life, we're going to take these little grids and we basically stack them on top of one another, and then we animate it by flipping it through kind of like an old school little cartoon. In the one-dimensional version, we're going to have that initial generation be the top row of some array, and then we're going to begin just appending new things to the bottom of it. The way that new things are going to be generated is still going to be based off of whether or not that cell was alive and if its neighbors are alive or dead. So you can see that we're going to have kind of a little block of 3 things. So you have you sitting here, we have the person to your left, and we have the person to your right. What happens to you then is going to be dependent upon some set of rules. So typically these rules in this 1D version are printed out in these nice little tables. So this particular rule is called rule 30, because 30 in binary is 0, 0, 0, 1, 1, 1, 1, 0. And you can see that that little kind of Tetris piece is going to tell what happens to you in the next generation. So this scenario then says if you're currently alive and your neighbors are both alive, then you die. The second one says you are alive, your left neighbor is alive, the person to your right is dead, so then you die. This third one says you are dead, your neighbors are both alive, which means you stay dead. This one then says your neighbor to your left is alive, you are dead, the person to your right is dead, so then you come back to life, and so on and so forth. So that top part, so that structure of those little 3 blocks, of which there are 8 of them, we're going to keep those the same. So the idea of 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, and 0, 0, 0. So we can represent these numbers up to 7 fairly nicely. And then the 0, 0, 0, 1, 1, 1, 1, 0 structure is telling me what's going to happen on the bottom of that little Tetris piece, basically what's happening here. So you can think about this as like a big old if structure. It's like if this random stuff occurs, then you're going to be either alive or you're going to be dead. And then what we can do is we can begin seeing what's going to happen in future generations. So down in the bottom, I'm going to have 2 examples of me running this rule of 30. This left one is where we start with a single alive cell and everything else is actually going to be dead. So then we play this thing in this downward direction. So right below that one, it's going to stay alive based off of that rule. So that's why that thing is alive. If I study this thing, you see that above it, it is blank, blank alive. So it's going to be that rule for why this particular thing is alive. The other side, so this one right here, that one is alive because above it is alive, dead, dead. So that is this rule. So you can see this kind of cute process going on downward. Things get a little bit more interesting as we go farther and farther down. So in this next level, if I wanted to think about why is this one alive? Well, above it, it is blank alive alive, and blank alive alive is this thing, which is why that one turned on. So you're always going to essentially look above and then left and right and then identify what's going to happen in that cell. This one right here is dead because above it is triple alive. So it's that rule, and so on and so forth. I actually do have a couple implementations for us to play with, and it becomes fun to see different starting scenarios. So this is what happens if you have an initial singleton in your start. This one over here is going to start if you have 5 things alive, and it creates a slightly different triangle on the back end. Your game is to play this with this rule of 90. So it's going to be the same little Tetris configuration, but the numbers on the bottom are different. So it's 0, 1, 0, 1, 1, 0, 1, 0, because that's 90 in binary. So you can see some of the properties are the same. So these ones match. These ones are now different. So if I had alive and the thing to the left as alive, then I'm going to stay alive here. These ones are the same rules. These ones are the same rule. That's the same. This one is now different. So if I'm singly alive and I have no neighbors, now I'm going to die where previously we lived. This one is the same and this one is the same. So we've changed 2 of the bits from 30 to 90, and it's going to make very different little triangle structures on the back end. I'm probably going to jump into the code for that one. The other ones I'll kind of let you explore your own code, and then I'll probably give this a pause as I jump to the last couple of videos. So let me do a swap screen. So this should be living in Safari Land. Give that a sec to think. All right, so it's going to be that same MATLAB plotting thing that we saw in the Game of Life world. So if I let this think, this is going to print out the rule of 30, this neat little, I guess, triangle of things. So the way that I've designed this is I'm going to have a big list called data. So it's a list of lists, and it's initially going to start with 40 zeros, a 1, and then 40 zeros. So that's the top of that row is going to be. So it's what, total 81 entries in that top row. And then I'm going to begin appending new rows to this thing. And this is not the most efficient way to go about this. So the hope is that you can take this and make it your own. This rule of 90 then is going to play off of those things of that sometimes I'm going to be alive in the next state. So my new row I blanked out is all zeros. So it's going to be 81 zeros. And then if I fit some of those requirements for this rule of 30, so if the person to my left is alive, the person above me is dead, and the person to my right is dead, then I'm going to spring back alive. So you're going to see that is just basically an if structure. So that little block of 3 things, well, that very naturally becomes entries in this little grid. So to the left, middle, and right, and those are going to dictate if I become alive. So in all of these, my new row is then going to become a 1, and in all other scenarios, this is going to stay 0. So I can run this thing to see that crazy little triangle that I just hand sketched out. You could change that data to then have a block of zeros with 5 ones in the middle. And if you re-execute that thing, wait for a second because it takes a little bit, you see a very different structure emerge on the back end. The rule of 30 is actually pretty fun because it's very chaotic. There's all kinds of weird scramblings and whatnot. In fact, the Wolfram language, so the things behind Wolfram Alpha and kind of Wolfram's Mathematica, they actually use this rule of 30, this kind of crazy structure that emerges, as the background of their pseudo-random number generator, at least for really, really big things. So you can kind of see its chaotic structure down on the bottom is that there's no real uniformity that exists there. In the rule of 90, you'll see a ton of uniformity in that. So if you want to change up these rules, you can very easily convert this to the rule of 90, and you'll see a very classic triangle. So there's going to be this fractal structure that exists on the inside, which is super duper neat to look at. And there's just fun pictures that emerge with that as well. So I'm probably going to pause it there because then we're going to jump into the last couple of questions, which are all going to be dealing with matching. So I will let us just explore those as we see fit. So see you in a couple minutes.